Hopefully it's fine. Yeah. Yep. Okay, ready? Sounds good. So my name is Victor. Yeah, I'm currently a PhD student in Colorado at the University of Colorado Boulder. But I'm originally from Spain, so it really is my honor to be back here sharing my work in my home country. I'll start with an introduction and then I'll get into the outline of my talk. So traditionally, when designing controllers for autonomous systems, the focus has been mostly on the property of stability, designing controllers that will guarantee the system is stable. Through the long history of control theory, I'd say that problem has been pretty well studied at this point. In the literature, you can find stabilizing controllers for pretty much any system that you want to stabilize. However, safety, which is the purpose of this workshop, is a newer concept that is currently under study in the literature. And control barrier functions are a tool for certifying safety. In control theory, the subfield that studies this property of safety is called constraint control. And the most famous example or approach in constraint control is model predictive control, MPC, where the algorithm predicts the trajectory of the state and will pick the optimal control law that will also guarantee safety. A different approach is safety filters, and they have this two-step approach where there's a nominal controller that has no regards for safety. It just enforces the stability or performance requirements that you want. And then there's this external force that guarantees the safety. So just to dig deeper into that, the safety filter approach, again, it's this two-step approach. First, you design a nominal controller for the unconstrained system, so without regards for safety. And then you introduce an add-on unit that will enforce the safety. And control barrier functions fit into this scheme. A control barrier function is like a safety filter that will take your nominal input and give you a safe input for your system. So that's the broad overview of kind of where CBFs fit within the broader control literature. I am going to begin by mathematically defining safety. And to start with that, let's take a look at the constraint control problem. So this is, in broad terms, the problem that the constraint control literature tries to solve. So we're going to consider systems in control-affine form. So dynamics of this type, this is what the CBF literature considers. It's a very general class of systems. For example, here's the quadcopter with 9 states. The dynamics, you can put them in this control-affine form. Okay, this is the full nonlinear dynamics of the quadcopter with 9 states. Here's another example that I'll use later in the presentation. So here's the F16 pitch dynamics with the short period approximation. That's a linear model for the pitch dynamics. Any linear system is going to have that control-affine structure also. Okay, so now we understand the classes of system that this problem applies to, and then we have the constraints on the state and on the input. So for the example of the F16, for example, the constraint is a pitch pointing constraint. So we want the flight path angle and the pitch angle to be well aligned. That's the state constraint, for example, that you could have. And also the input constraint in this example could be the control surface deflection. So the elevator and flaperon actuation limits. That's what we're going to call the state constraints and the input constraints. So finally, the constraint control problem is asking us to find an admissible input signal that will keep the state in the state constraints for all times. That's the constraint control problem that generally the constraint control literature addresses, trying to find a solution for this. Now, that problem might have multiple solutions. How your state achieves your desired goal within those bounds is what we're going to call the performance of your approach. You can remain in the constraint set, but maybe not achieve your goal. That's bad performance. So, is there a solution to this constraint control problem? The answer is yes, if your constraints are what's called control invariants, if the set is control invariant. So what is a control invariant set? A control invariant set is a set where if you start in the set, there is an admissible input that will keep you in the set. It's essentially restating the constraint control problem into a definition. So what if the set is not control invariant? What if there's an initial condition in that set where if you start there, for any input that is admissible, you are bound to leave the set. Your dynamics will just naturally push you out no matter what you do in control. Is there no solution then to this constraint control problem? No problem. The answer is no, that we still might have a solution to the constraint control problem. So let's imagine we have a different constraint control invariant set, the set C that is control invariant. If that set is admissible, that's what I call the set when it's a subset of our constraints, it's admissible, then there is a solution. We just remain within the set C, which is itself inside the set X, and so we have a solution again. So such a set C is what we call a safe set. That's how we're defining safety. It has these two properties, invariance and admissibility. Now, the control invariance property that I'm talked about, I said is essentially a restatement of the constraint control problem that doesn't give us much leverage for trying to find sets that are control invariant. So in 1942, Nagumo provided us with probably the most famous characterization of control invariance in his theorem. This is a simplified version of that theorem, and it provides if and only ifs and necessary and sufficient conditions for a set to be control invariant. Let's go slowly through that theorem. The first part is saying that this theorem, this characterization applies to a special type of set. This set needs to be defined by a continuously differentiable function, h, which has regular value 0. And the set takes positive values inside of that function and negative outside, and is 0 at the boundary. Essentially, these conditions require the boundary of the set to be smooth, to not have kinks. Okay? So when that's the case, the next part, the characterization, is called the subtangentiality condition. Let's go slowly through that. The beginning is for any point in the boundary of the set. That's what this partial C means, the boundary of the set. So the set of points where h of x equals 0. There has to be an input such that this condition, L of h plus LGH, is greater than or equal to 0. Now, what is LFH plus LGH? Those are the lead derivatives of the function h along the vector fields f and g. Okay, sounds complicated, but it's just notation. LFH is the partial derivative of h times the vector field f. So we can expand it. They're on the right side of the slides. And we can factor out the partial h, partial x. The right-hand side there, the f of x plus g of x times u, that's our dynamics. That's the derivative of our state vector, right? Because I said we have control of fine dynamics. And this is, by the chain rule, just the time derivative of the function h. So what is this condition saying? When we are at the boundary, meaning when h equals 0, the time derivative of h has to be greater than or equal to 0. So you have to have an input such that h dot is greater than or equal to 0, and you're going back inside the set. That's how invariance is being enforced intuitively. That's what this condition is saying. The main drawback, you could say computationally, for this characterization of control invariance is that the boundary of the set C is measured 0, and that is difficult to check numerically. Like imagine you are testing points in the plane. How likely are you to hit exactly the boundary of that set? Essentially probability 0. So that's the intuition for the difficulty of applying Nagumo's theorem in practical examples. Control barrier functions address exactly that drawback by extending these characterization of control invariance to the entire set, not just the boundary. So that helps us computationally to enforce this subtangentiality condition. So what is a control barrier function, as it was defined in the literature by the original authors? We're going to take a look at the original definition that was proposed by Ames, Pingree, Grizzle, and Taboada in 2017 in the original paper. That's the definition we're going to use here. And it has two parts. The first part, I call the candidate CBF part of the definition. And it's essentially the same initial condition, the same conditions on the set that Nagumo had in his theorem. It's saying you have a function h that is continuously differentiable, and your set C is defined by that function. It's positive inside, negative outside, 0 at the boundary. The second part is the CBF condition, and it's that subtangentiality condition, but now extended to the entire set. So let's go slowly through that. The first part, it says there exists a class K function, alpha. What is a class K function? A class K function is a type of comparison function that is continuous, strictly increasing, and 0 at the origin. So here I've given you an example, s squared over 1 plus s squared. That's a class K function. So is this linear function, cs, c times s, where c is a positive constant. In practice, pretty much all of the class K functions we're going to use are going to be of that form. We just take a positive number, and that's a class K function. So the second part. Let's try to understand this condition by just looking again at the boundary of the set. So if we put ourselves in the boundary of the set, h of x is 0 at the boundary. And because alpha is a class K function, this term vanishes entirely, right? Alpha of 0 is 0. That's what a class K function is. So what do we have now? Exactly the conditions of Nagumo's theorem. And so immediately, I have proven to you that if h is a control barrier function, the set it defines is control invariant by Nagumo's theorem. Now, Nagumo's theorem was an equivalent characterization, necessary and sufficient. So this is only giving you one direction. What about the other direction? If you have a control invariant set, do you immediately have a function h describing that set being a CBF? And the answer is yes, but there are some technical requirements that are beyond the scope of this workshop. Essentially, the set C needs to be compact, and also a more technical requirement. But there is a way of doing the same equivalent characterization that Nagumo's theorem gave us. So going back to the constraint control problem, a solution, I told you earlier, exists if we have a set C that is safe, meaning control invariant and admissible. A solution exists then. And I've just told you that if we have a function, a CBF, h, the set it defines is control invariant. So if you have a function h whose super level set is a subset of your constraints, and that function h is a CBF, you also have a solution to the constraint control problem. So now, if someone gave you a CBF whose super level set is admissible, you have a solution to the constraint control problem. Okay, but how do you actually find that solution? How do you find that input? That is what the CBF-based safety filter does. So now we're going back to that safety filter way of designing controllers. So here's the picture I had for that. Take the nominal input, filter it, and give you a safe input. What does it look like? What does that CBF block looks like? It's an optimization problem that looks like that. So let's understand that optimization problem. In English, in words, this problem says find the vector u admissible that minimizes the objective function, and that is a distance between the optimization variable u and the nominal controller, kappa of x. That's the nominal controller we designed without regards for safety, subject to the CBF condition, that LFH LGH greater than or equal to minus alpha of h. Now, looking at the optimization problem, each term that depends on x here is a constant for a given x. So even though they look nonlinear, and they are nonlinear, we are optimizing over the input, not over the state. So all these terms are just constants as far as the optimization problem is concerned. And the other constraint, the input be admissible, well, if that's a polyhedral constraint, so input constraints like that, like the F16 example constraints that I gave you on the flaperon and the elevator, are one type. In fact, they're even simpler than that, but they are polyhedral. Then the optimization problem becomes what's called a quadratic program. Quadratic function subject to linear constraints is a quadratic program. That's a type of convex optimization that we know how to solve very well. There are many commercial solvers that will solve this in milliseconds for hundreds of states. Very, very computationally efficient. And I think that is the main reason why CBFs have become popular in that practice and in the literature. How easy it is to solve the CBF-based safety filter. So this is a problem. Is there a solution to this problem? If the function h in the problem is a CBF, the problem is feasible. That's what we call feasible. It has a solution, as long as your state is inside the set C, the super level set of the control barrier function. And the proof is immediately in the definition of the CBF. Look at that. For any point in the set C, there is an input admissible such that this condition holds. So giving a little bit of an abstract figure for what this means of the whole safety filter approach. Let's imagine we have a system, we've designed a nonlinear, we've designed a controller for it without regards for safety. Maybe that's the performance of our system. It's violating the constraints because we didn't care about them when we designed the nominal controller. The CBF comes in and filters out that unsafe behavior and enforces invariance of the set C, not of the set X, but of the set C. Now, how big the set C is what's going to determine your performance. You can imagine we want the biggest possible set C that is contained in X to recover as much as we can the performance of the nominal controller. So at this point, hopefully the only question remaining in terms of this whole framework is how to find a CBF. Because once you have it, I've pretty much given you how to find the controller and all the guarantees you get with them. Now, that is the question that the literature is still trying to address. And if you know Lyapunov functions, it's the same. How do you find a Lyapunov function? Well, who knows? You just try for different systems. There are some approaches. Okay, so it's, I would say, a question that probably many of the speakers of this workshop are going to address, maybe for specific systems. It is the question that my PhD, the entire PhD, is trying to solve. Because nothing I've presented was my original work. I'm just giving you the background. But that's a question that my PhD addresses. So I'll give you through the example of the F-16, what happens in practice most times, how people design CBFs. I'll give you the drawback of doing it that way. So let's go back to the F-16, pitch pointing dynamics with the short period approximation. I'm going to augment them with an actuator inner loop to model that I cannot immediately command the elevator and the flaperon to go to a certain angle. So there has to be a delay there. That's all this augmentation is doing. But it has no importance for the CBF approach. So here I've plotted all the states, the pitch, the flight path angle, which is the pitch minus the angle of attack, the elevator and the flaperon. We're going to start from the cruise configuration. So flight path angle is 0. The nose of the aircraft, the pitch is slightly pointed up 2 degrees. And we want to transition to a climb configuration. So flight path angle 6.5 degrees, nose pointed higher at 9 degrees. Oh, I'm doing it time. Okay. For that, I'm just doing an LQR, linear quadratic regulator controller. So linear system, so I can just MATLAB LQR with a certain gain K. And here the U bar and the X bar are the desired target, the climb configuration. So the LQR transitions successfully from cruise configuration to climb configuration, but it does so without respecting, for example, the input constraints. The F-16 cannot do an elevator higher than 20 degrees or lower than minus 20. So it's not a very realistic simulation. What might we do? Well, we can saturate that LQR. That's one way of making the simulation more realistic and respecting the input constraints. First thing you might try, but look at the angle of attack now. It was violating our desired alignment with the nose of the aircraft, of the flight path angle and the pitch. We want these two aligned. That's what this angle is measuring, the deviation between those two. The nominal controller was already violating, but by saturating naively the controller, we've made that even worse. There's more misalignment. So let's try CBFs to design the controller. We're going to start with the CBF for the elevator, then the flaperon, and then finally the angle of attack. So what happens, again, remember, I'm presenting you what usually happens, not what I want you to do, but just this is what usually happens in practice, and it's going to work very well for many examples. So let's see. First thing, you take a look at the constraint, rearrange it, and look at that. You have a continuously differentiable function that is positive when you are safe. Good starting point. That's a candidate CBF. We just take the derivative with respect to the state to find H dot, to find this LFH, LGH term. So here I've put the dynamics. Here's the gradient of H. We can do those multiplications, gradient of H times A. That's just taking out the fourth row. So that's the 20 times elevator angle. And we can do the same thing for the LGH term, right? Just taking the fourth row. You can probably do this matrix multiplication in your head. That's what you get. So H dot is that term. And then we just enforce H dot greater than or equal to minus alpha of H. And put it in the CBF safety filter, CBF-QP it's called. And then, sorry, I went one too fast. This class K term alpha, we're just gonna take it as a positive number, like I told you before in practice, and we just tune it. We know it, we want it to be positive, and usually what happens is the bigger you pick it, the best performance you get. Smaller you pick it, the more safe your behavior is. is this trade-off. So back to the example, but I've zoomed in to the 3 constraint states. So angle of attack, elevator, and flaperon. I've removed the other 2 just to see the constraints better. Here's the elevator constraint. Only this one is being enforced in the CBF. And I picked alpha equals 30. So we satisfy that constraint and violate the others because I haven't done anything for them. We can do the same thing for the flaperon. The flaperon constraint doesn't change. The design process was pretty much the same. So pick alpha of 30 there again. And we're back at the pretty much the saturated LQR stage. We have comparable performance. So now let's do the same thing, but for the angle of attack. We can do the same thing. We can rearrange the constraint. And that gives us our candidate CBF. We can take the gradient and compute H dot. So for the term LFH, this time we're taking the 3rd row of the matrix A. For the term LGH, if we take the 3rd row, that's just zeros. So what happens? When this happens, say the function H there has relative degree higher than 1 when this term LGH vanishes. Okay? Why it's important is we've lost control authority there. That entire term is vanished. So when we want to enforce H dot greater than or equal to something, we've lost the ability to control that inequality with U. This situation is addressed most prominently in this paper that describes what's called exponential CBFs. I'm going to give you the intuition here for what they do in that paper, not the full approach. And the intuition is to treat this condition that we want to enforce, but we lost control authority for, as a new candidate CBF. We just rearrange it, set it equal to H1, and repeat the procedure. Differentiate H1 and compute H1 dot. So LFH1, we can do through the process. You can do the math yourself, but this term appears. I just plug it in. The term there on the right is going to cancel. This gradient H, this is original H times B. That's the 3rd row of B. It's going to vanish, so that term goes away. We get now something that's non-zero. We've recovered the control authority. So now we enforce this constraint, which will enforce this constraint, which will enforce this constraint. Okay? So for higher relative, this is relative degree 2, because I had to do this kind of twice. You could do it for higher, doesn't matter. That constraint is going to look like this, even through this higher order approach, which is still linear in U. And the 2 matrices look like that. That's A and B for the inequality. In B, there are 2 terms now, alpha and alpha 1. But you tune them the same way, pretty much. You can read that paper for more details. There is a more sophisticated approach you could follow, but you just pick positive values and then you'll be fine. So here I've picked 50 and 600. And I get something that now respects the angle of attack bound, as well as the elevator and flaperon. So now we've successfully transitioned from cruise to climb without violating our pitch and flight path angle alignment requirement. And perhaps most importantly, the approach to solve this problem, which you solve at each time, it only takes 3.5 milliseconds in my not very powerful laptop. So it's very much a real-time approach. Now, throughout the whole derivation in this example, I had this notice of this approach only yields candidate CBFs. Let me highlight to you what that means. So we transitioned from cruise to climb. Let's change that initial condition to transition from a descent. So instead of flight path angle 0, now it's slightly negative flight path angle. Nose also pointed down. and we want to transition to the same climb configuration. With the same LQR controller, we can achieve that. The saturation, respects the bounds, but doesn't do too good on the angle of attack as before. And if we enforce the same CBF safety filter that we had before, something bad happens. The approach fails. And by fails, I mean the optimization problem that we were solving to find the input becomes infeasible. There's no solution anymore. I told you this problem would be feasible, and it would be if H was a valid CBF. We only designed a candidate CBF. We didn't check that it was valid, so the problem became infeasible. That is the issue of designing CBFs naively, like we just did. You could tune alphas for this different starting point. You can fix this issue by tuning alpha and make it work. Here's the most aggressive alphas I could find that will make the problem work. Now the behavior is not very interesting. That's not very good performance. It takes forever for the F16 to transition. So you see this trade-off, but it's not even the trade-off that's important. What's important is that you have no guarantees that if you go back to the cruise, these new alphas will work there. You have no guarantees that even though you've tuned them now, you're essentially tuning for whatever your starting condition is. So if that changes, you might have to retune, okay? That's the drawback of designing CBFs naively like we just did. Regardless, it still happens a lot, and it's gonna give great performance in many, many examples, and you're gonna see CBFs do amazing things, even if you're designing them naively like this. So how can we do that? Design the CBFs not so naively. Question. Are you asking about, so this operated over 1 second. Are you asking about making alpha a function of time, sort of? Is that the, or the operating conditions? Yes, very good question. I have seen, and I'm sure there is many more works in the literature that address that. It might fall under the realm of adaptive CBF control. I am not going to present on that. I don't know if any of our other, maybe Johannes actually might present on that. So yeah, I think people are studying what if you change these alphas dynamically as the system evolves. So future speakers might address that issue. Immediately, I don't have an answer for does that work formally. Okay. Yes, I have no performance metrics at all for these alphas for any other operating condition. You have? This was an approximation of the system I'm doing, but the system itself, you're saying? Yeah. Okay. So now I'll go into my work in which I design CBFs that are valid and formally satisfy that definition that I presented. And I draw inspiration from the reference governor literature, okay? Just a different literature. So going back to the safety filters, we saw the CBFs operate here. The reference governor literature takes a different approach and filters a nominal reference to make the actual reference for the system safe. as opposed to filtering the input. That's the gist of the reference governor literature. The filtering happens at the reference level. So going back to the example where the CBF failed for the original tuning, if we change the reference of the LQR system to be something more mild, like let's say instead of from descent to climb, we go to an intermediate goal of just a milder descent. Now the LQR is going to achieve that easily, and importantly, it's safe. The whole transient itself is safe. You could think of this as, let's just not move and remain at this equilibrium or equilibrium operating condition. Great, so now we have dynamics that are safe but don't reach the point we want to reach. If we take a look at this distance, it's the minimum distance between the trajectory and the constraint. We can measure that for each constraint state. This metric, this distance, is what's called in the reference governor literature as the dynamic safety margin. Okay, it's the minimum distance to constraint violation for our pre-stabilized system. What Marco and I have shown is that this distance is a valid CBF that formally satisfies all the CBF definition when you consider an augmented system that concatenates your state and your reference, X and V. So we can treat those dynamic safety margins as CBFs and put them in the CBF safety filter and now find something that is safe and performs, I would say, quite well. We pay the price in the solve time because we have to rely on predictions of the trajectory, but still pretty much real time, 16 milliseconds versus 3.5 for this example. And if we go back to the original operating conditions from cruise to climb, so go back to the original initial condition, the approach works without any changing in the tuning. Our approach works. So that's it. I'm not giving you any more of my research. That's a tiny piece of what I've done, but it's probably the most exciting one. And none of that work would be possible without, my friends, my partner, my committee, and especially Marco, who is not here today, but he's been a great advisor. So thank you so much for listening to me, and happy to answer questions now. Yeah. Okay, so the question, I said we go to an intermediate operating condition. How do we get to the final one? Okay. This was just the intuition for defining the delta, the dynamic safety margin. You can define it formally like this and compute that numerically, and then enforce it as a CBF, and the actual transition does happen from the initial to the operating, like the whole range. The other thing was just intuition for what dynamic safety margin is. Yeah. Yeah. So if I'm understanding the question right, you're saying that in aerospace, the controller involves sometimes a pseudo-inverse approach, and that gives you a nominal controller for the performance that you want, I will say you can lump all of that information into this kappa of x and then put this on top to enforce the safety. So any legacy controller that you already have for your system, if it's safe, this won't do anything for it. It just returns kappa of x. Okay, so if your controller, if your legacy controller is safe itself, and you have a well-designed CBF, this filter will just let it pass through. Otherwise, it will filter it and give you the safety that you want. Does that answer you? Yeah. Yes, the computing your controller, if you're saying it takes meaningful effort, that can happen first before the safety filter even happens. Like, no matter how complicated your controller is, I assume you can compute it in real time to actually control your system. You have a number, that's the number you put in. Now, of course, this is very, very simplified. For many complicated parts, you might have to, break this up into multiple blocks, filter each block separately. You can do many things. I'm giving you a very, very simplified approach. But for any subsystem, if you have a nominal controller, a legacy controller that you like and gives you the performance you want, you can pretty much always, as long as you find a valid CBF, endow it with this safety properties. Yeah. Yeah. Question. Mm-hmm. Mm-hmm. Yes. Okay. I'll try to answer all of them. So the first question regarding naive CBF design with let's see if I can get. So the CBFs we designed for the F-16 only satisfied this part of the definition. I never checked that those functions satisfied the bottom part, which is actually the important part that guarantees feasibility of the optimization problem. I was enforcing this constraint numerically, but I never checked beforehand that that constraint will always be feasible. A CBF does that. Okay. Oh, so you're guaranteed that. Should I try to answer or take it offline?
Last question.
Yes.
Because with your naive might not check the formula. Please stand the same. If you start with the involved, this straightforwardly everybody will say, oh, just and call that our CBF. What he's saying is with that, you might, once you calculate extra, you might not verify the formula. Never check for that. That's why once you check, go for that.
Yes. And my work that I said with the dynamic safety margins does that. I have the formal definition that will satisfy that.